Hola amigos. So now let's move on to our next accelerated flight performance, that is landing performance. We know our aircraft performance, for which we have computed the ground distance up to the screening height of 15 meter. Similarly, we have the landing performance from the screening height of 15 meters till the touchdown ground towards the stopping of the aircraft on the runway. So just like the Indian guy who said bus land karwa do, here we will be doing a landing of our aircraft which will be gliding and approaching the runway by an angle gamma. Okay, by an angle gamma the aircraft will be approaching, and it will just flare for 3 seconds just like takeoff. And here at takeoff at landing it will just flare like this while approaching the ground, that it will just land on its rear wheels first, okay, and then it will align with the runway and move on taxing on the runway till it stops. Okay, so observing this gliding performance, here we have the concentrated mass, and on which we have plotted all the aerodynamic forces as we were doing in all our previous cases. Lift perpendicular to the flight path, okay, drag opposite to the flight path, along the flight path, and opposite to the direction of flight path, and thrust along the direction of flight path at an angle gamma. Weight always downwards. And point to be noted over here is that we know that fuel weight will keep on decreasing, and we assume that on landing the full weight of the fuel gets consumed, and that's why here we take the net weight of the aircraft at this screening height till this landing. Okay, and the net weight will be the weight of the aircraft minus weight of fuel. Okay, so observing this aerodynamic and this weight upon the aircraft, we have this tan gamma in terms of aerodynamic forces as we did earlier for the gliding flight, where lift is W net cos gamma, okay, here we have, and drag will be W net sin gamma, okay, component here we have, and the ratio of these two, d by L, will be tan gamma, okay, d divided by L will be tan gamma. If you take this vector and make it a triangle, like the triangle vector, then you will see tan gamma is equal to 1 by L by d, and it can be substituted in terms of CL by CD, or you can use it as it is for computing the aerodynamic efficiency or performance parameter of an aircraft, because we know L by D is also an performance parameter of an aircraft. So we know the screening height is 15 meters, and till this point up to HTD, that is touchdown point, okay, this over the runway the aircraft will touch down, and this HTD is the height from touchdown to this bar. Okay, so 15 minus this height will be this gliding phase, we can say, and for this touchdown height we have this flaring distance on the ground. Okay, so here we have SA, on as we did in the takeoff performance, we measured the distance along the ground. Here also we will be measuring the distance along the ground, that is SA for the first phase, okay, and flaring distance on the ground for the second phase, and for the third phase we have the touchdown distance or the landing distance over here. So here we have this triangle, we can say, upon which we can see that tan gamma is perpendicular 15 minus STD upon base SA. So SA can be computed from this easily. So we know tan gamma can be computed from aerodynamic parameters, and SA can be known from this trigonometric relations. So there is another method that total energy of the system remains conserved. Okay, so how we can use this is that we know the kinetic energy and potential energy over here, that velocity at this screening height, velocity at h equals to 15 meters, is 1.3 times of v stall. Okay, v stall we know is velocity at CL max, okay, during a cruise flight, and for that lift is equal to 8, and from there you can calculate v stall, and 1.3 times of v stall we know now is velocity at height equals to 15 meters. And in the book, this velocity at height equals to 15 meters is also termed as touchdown velocity. Okay, touchdown velocity is also termed as the screening velocity at height equal to 15 meters. But the touchdown velocity is 1.15 times of v stall, as done by the A.K. Ghosh sir, who has done videos of aircraft performance in IIT Kanpur. So in his videos you will see v touchdown is 1.15 times of v stall, but in the book we are following is the touchdown velocity is v h equals to 15, v at h equals to 15 is 1.3 times of v stall. So here if we see that kinetic energy with this velocity and potential energy with this height, there's some minus the kinetic energy and potential energy at this point, where the potential energy will be 0 but kinetic energy will be some velocity. Okay, so velocity, you can use this as touchdown velocity. So their difference will give us the amount of work done from this point to this point. Okay, so that difference or the amount of work done can also be converted in terms of force into displacement, because you know the force into displacement is the amount of work done, and from there also you can compute the distance SA, horizontal distance. We are not doing it over here, but it is easily computed from this trigonometric relation, so we will not go into this. And moving on to our flaring distance, which is just for 3 seconds. Okay, so the aircraft was gliding with an angle gamma, and it approaches the ground and flares for 3 seconds and then touchdown. Okay, so for 3 seconds it flares, and here it touchdown. So for 3 seconds we assume that its touchdown velocity is 1.3 times of v stall, and then we say that s flare is 3 times of touchdown velocity. Here touchdown velocity I'm talking about is v h equals to 1.3 times of v stall, so do not confuse it with this touchdown velocity. Okay, so now let's move on to the third phase, where, and we know for the takeoff performance, the aircraft was accelerating from the start of the its from the start to the taking off point. Okay, so and from here, from the touchdown point to the end at where it will be coming to the rest, so it will be decelerating. In takeoff it was accelerating, and here it will be decelerating. So here if you see, the aircraft is experiencing okay, one more point I forgot to tell, that here if you see that thrust is assumed to be 0 for this gliding flight. Okay, because for a glider, the aircraft we are talking about is not specifically a glider for which thrust is 0, but we are assuming our aircraft is running at the lowest thrust, that such that thrust can be assumed to be 0. Okay, so if you know that the gliders are also powered by engines, so you can search about that. It is not necessary that a glider will not have an engine, it will be a glider with an engine. You can search about that more. So moving on to this touchdown distance or landing distance, SL or STD. Here you can see that the aircraft will be experiencing the lift, thrust, drag, weight along with the friction force mu. Okay, so and here we can assume lift to be 0, because as the aircraft is approaching the runway, it will have to decelerate, and subsequently it will have to lower its lift so that it could land, and upon that on that basis we can assume that lift is equal to 0 or lift is tending to 0. Here we can do that in the expression we will be covering now. Here we can assume lift to be equal to 0. So now moving on to this force, which is decelerating force from touchdown point till the end. It is decelerating and its deceleration is varying from the touchdown to the stopping point. Okay, so just like the takeoff performance, we took an average at 0.7 times of takeoff velocity. Here we are taking the average of deceleration with 0.7 times of touchdown velocity. Okay, so that is lift and drag. If it is given in the question there is some lift, then you have to put the value of lift in the question, otherwise you will automatically assume lift to be 0. So moving on to this, that lift and drag will be computed at this velocity, at 0.7 times of v touchdown velocity over here for the ground distance for landing. So it's a deceleration, therefore we have minus sign over here. So the aircraft will be moving in the forward direction, and thrust, as I said, can be assumed to be 0. Okay, for the whole flight. So here we have thrust tends to 0, and the force that is decelerating is minus t minus times of mu times of w minus l. Okay, so minus sign is taken common over here, and d plus mu times of w minus l, because the normal force will create a reaction of this friction. Okay, so this frictional force is mu times w minus l, and which is added with the drag in the direction of drag. And just like we know force is equal to mass into acceleration, here we know force is mass into deceleration. And from the Newton's second law, or Newton's laws of motions, we know v square minus u square equal to as. We know v is 0 over here, and s here will come out to be minus of some value. So upon using the acceleration value from here, okay, equals to ma it was, and acceleration was basically deceleration was taken an average for velocity 0.7 times of v takeoff, and this acceleration value is then substituted over here, okay, for v square minus u square equal to as. Okay, so from just like we did for the takeoff performance, we have done over here. You can just look at the takeoff performance video and observe what could be done to reach out to this formula. Here, point to be noted over here is that weight will be the net weight. Okay, here also weight will be the net weight of aircraft. So the touchdown distance STD is equal to the 1.69 times of w net square divided by rho infinity gs planform area of wing multiplied by CL max of aircraft multiplied by d. This is whole multiplied by d plus mu times w net minus l whole in for 0.7 times of touchdown velocity, which is 1.3 times of vstall, and this 1.3 times of vstall is multiplied by 0.7. Okay, for that velocity we compute lift and drag and put those values over here. So finally we have this touchdown velocity. There are two touchdown velocity, not velocity, touchdown distance. We have first one with 0 thrust. Okay, here this x direction is positive and this x direction is negative. So this is positive x direction towards which we have assumed the thrust to be 0. So let's say the thrust somehow is in the negative direction, so it should be added with the drag. So this technique of making the thrust acting opposite to the direction of aircraft, thrust is acting backward. It should be in the forward direction to move the aircraft in the forward direction, but it is acting backward in the direction of drag and dragging the decelerating aircraft. Okay, so the thrust which is decelerating the aircraft is known as the thrust reversal, which is represented by TREV over here. So it will be added with the drag over here and friction as well, as you can see, and rest remains the same. For touchdown distance, STD is equal to 1.69 times of W net square divided by rho infinity GS, same planform area of wing, CL max whole multiplied by thrust reversal plus drag times drag plus mu times W net minus L at 0.7 times of V touchdown. Okay, which means the 0.7 times of V touchdown will be used for thrust reversal as well. Okay, so with this the formula and all these have been done, but as we did for the takeoff performance, in the force and velocity variation we observed, basically v square variation and velocity variation we observed along the ground we have observed. So from touchdown to this stopping point, or say resting point, we observed that lift we know keep on decreasing, okay, till it reaches the 0 distance. Okay, so till it stops, actually s equals to 0 and stops, and lift keeps on decreasing and drag keeps on decreasing because drag is also a function of velocity. They are parabolic function of lift and drag are parabolic function of velocity. They are directly proportional to v square. And since we are observing lift and drag with respect to v square, not with respect to v, here we have the linear variations for lift and drag which are decreasing. Lift will be decreasing at a much higher rate with respect as compared to the drag. Just like lift increases at a higher rate, lift if plotted with increasing velocity will be like this. Okay, it will be increasing like this, whereas drag will be increasing like this at a lower rate with the velocity. So coming on to this, that lift will be decreasing at higher rate and drag will be decreasing at lower rate. And since friction is computed for mu times w minus l, the weight will be increasing because the lift is decreasing, so the friction will keep on increasing. So here we have this mu times w minus l, which will be increasing. So the net effect of this drag and friction is given by the increase of this backward force, you can say, okay, which is acting on the aircraft, that is drag plus mu times w. So we will cover the next topics, rest in the next lecture. Thank you.